seminar series. So today, just before we start, just a reminder about a few of the logistical items. We will be recording the talk, and when people log in, everyone will be muted. But if you have a question, please post them on the chat window, and we'll take them as we go. And the people who have registered for the talk will be getting an email later with the slides and feedback survey. So thank you for Lebauer. Today we have Dr. Lebauer, from an associate professor in statistics from Penn State. And Lebauer's research area is using statistical models to actually talk about, different types of health epidemic situations. So along the same line, today Lebauer is giving a talk about mapping distributions to marginalized groups. Lebauer, take it away.
Thanks a lot, Prabhani. Hello, everyone. Today, I'm going to share some recent work I did to help UNAIDS. I have been working on HIV epidemic for a long time. In the past 4 or 5 years, the HIV intervention is in the direction of focusing on the marginalized groups, such as drug users, sex workers. The difficulty is that we don't have enough information about those people. So there has been constantly some argument about why do you need to focus on those people? Do we really have those people in our country? So we did that in 2 ways. One is that we do a large map. We produce a large map for the entire Africa countries, so that we could have some idea about how many sex workers are there in the country or district. And in another example, we use the high quality data and produce the fine resolution maps. So today I'm going to talk about those 2 maps. They are joint work with my students, Sanam and Ian. Because I'm out of country, I was worried about the internet connection. So I recorded the talk first. And next, I'm going to play the recorded video so that if I got interrupted, like if there's internet issue, Prabhani can continue play that from her side. And while I play the video, if you have any question, I can pause and still answer questions.
Lebauer, I can't hear the voice. I can't see the video.
Okay, I think I know what happened. Let me. It has been more than 40 years since the first documented case of AIDS. Since the first case, more than 40 million people have died from HIV/AIDS related illness. Comparing to COVID, the total number of COVID deaths worldwide has been 6 million. So ending HIV/AIDS is still a big challenge to the global health. Global health is a little bit different from traditional biostatistics. Global health aims to reduce and end the inequalities. So it focuses more on low and mid-income countries and those who are struggling with health issue and limited resource. The new global AIDS strategy aims were discussed and approved at United Nations high-level meeting in New York in early June 2021, the 40-year anniversary of the first documented case of AIDS. This new global AIDS strategy aims to end AIDS as a global public threat by 2030. This will be achieved by a decline in the number of both new infections and AIDS-related deaths by 90% between 2010 and 2030. The evaluation details are quantified as follows. First, it is known as 390s. That is, among people who are HIV positive, 90% of them are aware of their HIV status. And then among those who were diagnosed, 90% of people receive treatment. And finally, among those who receive treatment, 90% achieve viral suppression, which means the viral load is very low in the body, so that there's no AIDS-related syndromes, and also the person is not likely to transmit HIV to other people, even through sex or blood. So this is also known as treatment as prevention in HIV strategy. And we also want to reduce the new infection from 2 million to 500,000 by 2020. And also we shall have zero discrimination towards people who are having HIV. And then by 2030, we want to raise those 390 targets to 395. And we want to further reduce the new infection to less than 200,000 per year. Next, let's take a look what we are doing so far. In the 2021 report, among all people living with HIV worldwide, 84% of them knew their HIV positive status. And 73% people had access to treatment. And finally, 66% were very surprised. In terms of the new infection, there were 1.5 million new infection. We only achieved 25% reduction of the new infection by 2020. So this number of new infection triples the target we set for 2020. And in the next few years, we want to further reduce the number of new infections to be less than 200,000. So that is a very challenging task. And we also know that HIV AIDS epidemic has received lots of attentions and large funding support in the past, for example, from Gates Foundation, PEPFAR, NIH, Global Fund. And nowadays, the budget will not increase for HIV intervention. And COVID also make things worse. For example, discontinued treatment and missed HIV testing. So under the new strategy, there is a shift of focus from the general population to the key population. And in today's talk, we will talk about female sex workers in Africa. HIV epidemics disproportionately affect certain geographic regions and subpopulations that are at higher risk of HIV based on their sexual practice, occupation, and substance use. They are a group of people with high risk of HIV infection, and those small number of key population accounted for 65% of HIV infection worldwide. Take female sex worker as an example. They are at 30 times higher risk of HIV infection and transmission than the general population. Therefore, reducing the new infection among those key populations is one of the most important strategies to meet the UNAIDS goals. In global health, people often say that what gets counted gets done. because where the problem is most severe, it's also where we know little about it. Geographically, Eastern and Southern Africa is the most affected region by HIV. Only 6.2% of world's population living there. However, 45% of the HIV infections and 53% of people living with HIV globally are in Eastern and Southern Africa. And if we look at the particular key population, the sex workers, more than 55% of female sex workers are estimated to be HIV positive in Eastern and Southern Africa. They are at increased risk of negative health condition in general, not limited to HIV infection. They also face discrimination in their communities, and due to those reasons, they are very difficult to locate or trace. On the right, we have the map showing that among almost all countries in Eastern and Southern Africa, they had different kind of penalties on the sex work behavior. So standard survey and census method are not good enough to understand such population because they are marginalized. We use the small area estimation method, and we focus on subpopulation and the sub-areas. Let's first take a look at the data availability in Africa. There are many areas where size estimates have not been done, or different studies offer very distinct estimates. We have put lots of effort on model diagnosis and data validation. So we performed a literature review for female sex worker size estimates in Africa countries. On this map, the gray color indicates country without any estimates, and the darker color indicates the country with more size estimates. For example, size estimates at different cities or at different districts. We collected 1,200 estimates across 39 countries at all spatial resolutions, at country level, province level, district level, or city level. Those estimates are clearly not uniformly distributed across countries. 4 countries have more than 100 estimates, and about half of countries have less than 10 estimates. They also came from 5 to 6 different data collection methods and corresponding different estimation approaches, which we shall also taking into account because different estimation procedure or sampling method may introduce different kind of bias. So we performed a meta-analysis based on existing female sex worker estimates, and now we have the estimated proportion of female sex workers by sub-national areas on the left and national level estimates on the right. The darker color indicates a higher proportion of female sex worker among the general female population. So this is the first map for key populations in sub-Saharan Africa. Note that those countries have been reporting the HIV epidemic among general population in the past 30 years. This map fills in estimates for areas with no study of key populations. Some countries would say they have 0 female sex workers, and thus they do not need to do size estimation or plan for intervention among the female sex workers. We argue that it is not the case if you look at your neighbor countries or if you look at countries with similar attributes, for example, demographic factors or economic development levels. So how does this affect the health policy? I don't know whether you have played the real-time strategy game before. In those games, the map is often covered by the cloud so that you do not know what other people are doing. And the good players constantly use resource to explore unknown areas so that they know what is going on this map. If you can open the whole map, then you make the game much easier for yourself. You have more information and you can make optimal strategy for managing your resource and building different kind of units. Fighting HIV or other global health disease is in the same situation. We need detailed maps for prevention, intervention, and treatment planning. So the figure we presented here, the finance resolution is at the district level. This has been published in the PNAS paper. However, most areas do not have high resolution estimates to guide the health policy. So the next study based on higher data quality countries provide an example of guiding the policy with high resolution maps of female sex workers in the limited resource setting. On the right, it's a map of Malawi, which is made up of 28 districts. In 2016 and 2018, the University of North Carolina implemented a so-called PLACE study, which stands for Priorities for Local AIDS Control Efforts. The study estimates female sex worker size using local surveys and produce estimates at the district level. And in our approach, we can do better than district level estimates. We build on the protocol in PLACE study and incorporate additional information such as auxiliary covariates in a regression framework. The PLACE study works by focusing on venues, which are locations where people meet new sexual partners. This includes bars, massage parlors, guest houses, brothels, and so on. Specifically, the PLACE procedure is divided into 3 stages. First, they compile a list of all venues in each district by interviewing people and holding consultation meetings. Second, they visit a subset of those venues and record the number of female sex workers through interviews with venue staff. Finally, for each district, they calculate the number of female sex workers per venue based on those visited venues, and then multiply it by the total number of venues in the district to get the total number of female sex workers in the district. We can see the basic formula in this equation, where J represents the district. However, this approach has 3 limitations. First, it assumes unvisited venues and districts behave similarly to visited venues and districts. Second, aside from visited venues, the number of female sex workers is estimated only at the district level. And this estimate is not good enough for people to implement the prevention at the more local level. Third, there's no sharing of information between the districts. And next, I'm going to present our proposed method, which overcome all those three problems. Let's first take a look at the place data in more detail. The place data contains three pieces of information. First, we have the longitude and latitude of visited venues. Second, at each visited venue, we have the number of female sex workers who work at the venue. Finally, due to the the initial consultation meeting at the community level, we also have a rough number of the total number of venues in the district. So on the right, we have a map visualize the visited venues in Balaka, a city in Malawi. We can plot each venue as a point, and the color of venues represents the intensity of the venue, or how many female sex workers were recorded at each venue during the interview. To get the fine resolution map, we begin by discretizing Malawi into roughly 50,000 cells of size 1.5 by 1.5 kilometer. And this figure shows a lower resolution map with only 5,000 cells. The venue size is defined as the number of female sex workers at a venue, and the venue count is defined as the number of venues within a cell. And in this second figure, we simply count the number of visited venues in each cell, and blue color indicates there's no venues, and the bright color indicates there are more venues. And finally, the quantity of interest is the number of female sex workers within each cell. And this is obtained by multiplying the venue size by the number of venues in the cell. There are several challenges when we produce the fine resolution map. The first is that the response variable and the predictors are not available at the same spatial scale, and this is known as the spatial misalignment. For the auxiliary variables, we have nightlight, word pop, as well as demographic and health survey data. The DHS data collects various household information, including annual income, age at first sex, education, wealthiness index. Those variables are measured at 850 clusters around Malawi and include covariates like literacy, and this is the map we show on the left, where each dot is the center location of a DHS cluster, and the bright color indicates a higher proportion of people who can read within that cluster. And then the nightlight data is recorded at a fine spatial resolution via satellite, and the intensity approximates the local human activity. And finally, the word pop measures the population size at the 0.1 by 0.1 kilometer cells. To deal with the spatial misalignment, for the DHS covariates, we use universal kriging, which assumes spatial linear function with respect to longitude and latitude, and with additional mean zero Gaussian process. The smoothed result is presented on the right. Again, bright color indicates a higher proportion of literacy. For the nightlight and word pop, they are available at a smaller resolution than our place data. So we just average the nightlight and population size within the unit of the place data. After this procedure, our response and covariates are all available at the same cell level, which is 1.5 by 1.5 kilometer. Another issue comes with this place data is that the response is zero-inflated, which means the number of zeros is extremely large. It's not hard to imagine that in most of those 50,000 grid cells, most of them, no one lives there, and therefore we do not expect to observe any value in those cells. And for the value size, although they come up with some potential values that would have female sex worker, but then during the visit, they found that many of those values actually do not have female sex workers. So what we do is that we assume value count and value size follow zero-inflated distributions. And the zero-inflated distribution is essentially a mixture model where the response with probability P comes from a point mass 0, and with probability 1 minus P coming from a count distribution with probability density, probability mass function F. And then the observed zeros can come from either the excess zeros with probability P or from the count distribution. Based on several diagnoses, we assume a negative binomial distribution for F, and the probability mass function is defined in equation 3. It involves the over-dispersion parameter phi and the mean parameter mu. Oops. So here, yi size is the observed value size in cell I, and pi size is the probability of excess 0, and mu I is the conditional mean for the negative binomial distribution. And both pi and mu I depends on some selected explanatory variables with fixed effect, and also some variables with country level random effects. And finally, we also have the district level random intercept denoted by this gamma di, where di represents the district that cell I belongs to. And if you remember, the DHS variable involves many hundreds of potential covariates. So there is an issue of variable selection. What are the covariates we want to include in this regression model? And we deal with that in the Bayesian setting. We perform the Bayesian penalized regression with a house-rule prior. The house-rule prior assumes that the coefficient beta k follows this normal distribution where the variance lambda k follows a half Coset distribution. So the idea is that we put a large amount of shrinkage for beta k towards 0. However, this prior distribution also allows the true non-zero beta to escape from the penalty due to its heavy tail. And the first issue is that for in the place data, we don't know the location of unvisited values. So we only have information about the positive response. We may assume that the value size is missing at random. However, we cannot assume the value count is missing at random. So this is known as the presence-only data. And for cells with 0 values, we don't know if this is because there are actually no values in the cell, or it is because we did not visit those values. And also for values with positive count, there can be issues of underestimate, because if in one small area, if there are too many values, they may choose to only visit a subset of those values. Therefore, the number of values shown on the map with longitude and latitude is underestimated. So here we offer a very brief literature review of methods deal with presence-only data. One of the oldest methods, but still very popular, is called the pseudo-absence model. Those models rely on simple random locations, sampling randomly sample locations with 0 counts across the domain, and assume that they are the true absence. And then they fit the model on the combination of observed positive counts and those pseudo-absence counts. In this project, we extend the pseudo-absence approach, and we incorporate additional information, such as those auxiliary variables and also the information about the total number of values within a district that were discussed at the initial consultation meeting. So here, we assume that the true value count follows a zero-inflated negative binomial distribution, as we have discussed before. But we introduce another thinning process. That is, each true value can be only observed with probability pi. And this probability varies by district. And because for each district, we know the total number of values. We also have the number of values being visited. So this pi is the sampling probability for district DI. The proposition 1 basically describes the thinning process. And then we show that this thinning operation does not affect the 0 component. It does not affect the probability of coming from a point mass 0. It only affects the count distribution F. And then we further show that if the true value count follows a zero-inflated negative binomial distribution, then our observed data, the observed value counts, also follow a zero-inflated negative binomial distribution. The mixing probability P remains the same. The only difference is for the mean of the count distribution. And we can easily adjust the difference by adding one more term to the log of mu I, which is log of the sampling probability for district DI. So now we can summarize the connection between all the data sources and our model. In order to build the value size model, we only use the value sizes and the auxiliary variables. To build a value count model, we use value locations, which are translated to the number of observed value at each cell and the auxiliary variables at each cell. But we also calibrate the model so that the likelihood represents the actual number of values in a cell. And we calibrate the model using the district level value counts. Finally, as just mentioned, these two models come together to give us a female sex worker size model. And it comes from the product of estimated value size and estimated value count. We look at the residual plots for the value size residual and value count residual, and those two sets of residuals are fairly independent. So the final total number of female sex worker at each cell is essentially utilizing the information of those 4 data sources. Finally, we have the issue of the computation time because of the very large number of grid cells in multiple countries. The value count model at cell resolution involves more than 800,000 grid cells. And for most locations, there is no value observed. We call the cases the cells with positive value counts observed, and controls being grid cells without any value that may have female sex worker. In order to speed up the computation, our general idea is that we keep all the cells with non-zero value counts. And for those cells with 0 value counts, we take a simple random sample. This idea has been widely used in epidemiology. It is known as the case control study, in which the cases are too rare to do a simple random sampling for the whole population or conduct a cohort study. And the solution is that we keep, for the rare disease patients, we keep all of them. And then for each patient, we choose about 5 to 10 controlled samples from the disease-free population. And a very good result for the case control study in the logistic regression is that all the regression coefficients except the intercept would remain the same no matter what when you do the case control study or you do the whole population study. And the intercept can be adjusted if you know the true prevalence of the disease in the population of interest with this formula. However, case control has never been implemented for the zero-inflated models. So next, we would show that this idea is can be easily applied to the zero-inflated models, and we can always undersample those 0 counts as long as conditional on each covariate, the proportion of observed zeros in the sample would be larger than the probability of y equals to 0 for the count distribution. In other words, we need to make sure it is still a zero-inflated model for any value of covariate. And the case control sampling does not affect any parameters in the count model. and it only affects the intercept of the logistic part, which controls for the proportion of exceed excess zeros. So we conducted a simulation study. We simulate from a zero-inflated model with 250,000 data points. Approximately 90% of data points equals to 0. And we very aggressively remove 95% of the observed zeros. We use a very simple model where the logistic part has two parameters, an intercept and a slope. And the count model also has those two parameters. And we repeat this simulation study 100 times. So this table first shows the true value of the parameters, and then the mean value of the point estimates across 100 simulations. We can see that the mean value is fairly close to the true value. And the standard error, standard deviation are reasonably small, while the coverage of the 95% confidence interval is doing okay. Next, for the real data analysis, the place data involves less than 1% of cells that contain the positive counts. We aggressively undersample those zeros, and without the case control idea, model fitting using all of the data takes longer than 10 days. And after we took a subset of zeros, the model fitting now took less than 5 hours. Finally, we can look at the results for the place data analysis. For the variable selection, the first round, we only consider the models with fixed effects. For the venue count, we obtain 10 variables in the negative binomial part and 15 variables in the logistic part. And for the venue size model, we got 7 variables in the negative binomial part and 14 variables in the logistic part. And in the second round, we further consider whether some fixed effects may vary across districts or countries. So we try to add additional random effects. The venue count model finally select 3 variables with random effects for the logistic part, and venue size model chose 2 variables with random effects. And this is the proof of the independence assumption between the venue count and venue size, as I mentioned before. Those residuals looks fairly independent. The correlation is less than 0.02. Checking the performance of the presence-only model is not an easy task because we don't know the truth at either cell level or the aggregated level. However, for the place study, we have a few districts where the place team visited almost a very large proportion of the venues they came up at those consultation meetings. So we focus on the districts where the proportion of visited venue is greater than 85%. And we consider the district level estimates produced by place team as the gold standard for those districts. In those 2 figures, the dots are the estimate produced by the place team, and the bell-shaped plot corresponds to the posterior predictive distribution for the district level female sex worker size. And we can see that the blue bar, which is the posterior mean, is reasonably close to the estimates provided by the place team, and the coverage of the posterior predictive interval also looks okay. On the left, we take one district as test data at a time. Therefore, it is one district out of sample prediction performance. And on the right, we also consider the situation that we remove all the data from one country. This allows us to investigate whether we can make prediction to another country without place data. Again, the point estimate, which is the vertical blue bar, it's close to the place estimates for many districts, but the uncertainty is much larger for all the districts because we do not have country-specific data points allow us to reliably estimate those country-specific random effects. Another measure we look at is the posterior predictive p-value. So basically, for each posterior sample of the parameters, we generate the data again, and we calculate some statistic for each sampled data, as well as the true place data. And the p-value is essentially the quantile of the observed statistic among those sampled statistics. And a large or small p-value indicates some violation of the model assumptions. So the statistic we considered include the mean value of the positive counts in the data, the standard deviation of the positive counts, the over-dispersion index, the maximum count, and the proportion of zeros. And we do that for value count as well as value size. We see that the p-values are all close to 0.5, indicating there's no violation, at least from the perspective of those statistic values. Finally, the most important result of our model is those cell level estimates. So they are provided at 1.5 by 1.5 kilometer grid cells. However, for the privacy reason, in our publications, we only show results at a lower resolution, which is 5 kilometer by 5 kilometer. So on those figures, on the left, we have the estimated distribution of female sex worker for Malawi. And this is based on using data from all the 4 countries with high quality place data. And on the right, it is the female sex worker distribution predicted by using other place countries, but excludes the data from Malawi. And we can see that the 2 maps are roughly similar, suggesting that our method can potentially be used to extrapolate the female sex worker distribution, even if they have even for the country that have not conducted a place study. And this is the similar figure for another country, Angola, which has a much larger geographic area. However, there are much fewer urban areas or cities in Angola country. So now we can wrap up this talk with some conclusions. First, this is a fully model-based approach for modeling the presence-only data. And in addition to the auxiliary variables, we also properly include the information about the total number of venues within each district. We have a large number of potential predictors. So we use Bayesian methods to perform the model selection. Our model also include random effects at different levels to account for the additional heterogeneity. Finally, a case control sampling strategy is introduced for the zero-inflated model. It is necessary because we are fitting a mixture model, which involves both logistic part and count part. And also, the model is generalized linear model with many random effects. And we have a very large number of grid cells. All those together makes the computation very challenging. This is the first study to deliver a fine resolution map of key population across multiple countries. Even when no place data is available, this approach can potentially predict the geographic distribution of female sex workers with the help of identified explanatory variables. The result is still not perfect, and there could be disagreements about the estimates we produce. However, we think this is a starting point of the conversation between statistical models and the health policy. If there is doubt about our particular estimates, then we can look into what kind of additional data that shall be collected, or which model assumption needs to be further validated. Our study is a call to action for more accurate and extensive estimates of female sex workers. And those results should not be viewed as a substitute for the primary data collection effort. This work is supported by an NIH grant. Thank you.
Thank you, Lebao. I think so. Since Lebao is here, if anyone has particular questions, they can just unmute yourself and ask the question.
Thanks. I first saw the question from Prabhani on the chat. Does place data has actual observations? I think it can be considered as actual observations because we have some venues, and at those venues, they ask people who works there, or say the owner of the venue, and figure out how many female sex workers are there. However, there will be some underestimate about the venues, because for some location there could be venues, but they didn't visit, and we don't have a record of the geolocation for the unvisited venues.
I see.
So it's like partially observed.
Okay. I have another question, I guess, a little bit of a naive question maybe, but when you are extrapolating from to the countries that you haven't observed any place data, does your model have a tendency to always overestimate, or is that just the two examples that you showed? Because to me,
you're right. Mm-hmm. We
Sorry.
didn't check like the out of country prediction, whether it is consistently overestimate or underestimate. I can move to that figure quickly. So what we can tell is that it has a much larger uncertainty because the model involves country-level random effects. And for the out-of-country prediction, basically we sample the random effects just from the prior distribution. And I think maybe it is because it has the posterior samples has a very large range, so that it raises the average prevalence. It increases the posterior mean.
Okay.
Yeah.
Okay.
Hi, Le. Thank you for
Yeah,
the great talk. Will you please provide some intuition about choosing the prior?
Well, choosing prior. So wait. So this is the prior distribution we chose for the regression coefficients, and there were also some hyperparameters. We didn't play a lot with the choice of hyperparameters, but this prior, basically the idea is that it can do the automatic variable selection. It is like Bayesian lasso or ridge regression. Yeah, we didn't use some other like empirical base or those kind of approach.
All right, any other questions? Well, thank you very much, Le, for a great talk. Just as a reminder, you'll be getting a survey, a link to the recorded video, as well as link to the slides if you are registered sometime later in the week. And we have our next talk on February 13th. Hope to see you guys there as well. Thank you. Thanks, Le.
Thank you.
you.
Thank you. Yeah.